Thank you. Hello, everybody. Today, we're going to talk about the component anatomy, 90 degrees to the left. My name is Alain, and I come from the Congo-Brazzaville country in the middle of Africa. I live in Paris, and I work as a software engineer at BAM. And you can join me in my social network. So, as I say, we're going to talk about the component anatomy, which is an empirical and descriptive approach of the architecture I've been working on for many months. It's highly inspired from the layered architecture, the clean architecture, and the atomic design, and firstly made for junior developers. So in this talk, I will start by relating the origin of the component anatomy, and then we are going to compare both programming and construction industries, because I have a conviction that developing a mobile application is quite similar than building a digital house. So I will explain you how I switch from my old approach of designing a component to the component anatomy itself. And then I will share with you the potential usages and the feedbacks I started to receive. As I said, I work at BAM, and at BAM, before developing any features, we start by listing any updates, all the updates, to apply to the code in order to deliver the feature in the best delay and with the expected quality level. And we call this exercise the technical strategy. Okay. This exercise requires to anticipate the complexity of the code to be developed. And for many reasons, I won't enumerate here. The strategies of my team and I was not perfect, and the collaboration was not optimal. So it led me to seek for a tool that could help us to visualize the complexity of the code, to enhance the quality of the workshop, and to get a better scheduling of the work to be done. In addition to these problems, I was also thinking about bugs. Why bugs? Well, in a previous project I've been working on, we faced many issues with cross-screen features, and I noticed that these issues were only related to a bad architecture, or to be more specific, to the absence of a global architecture. For instance, you know this kind of moment when you change a part of your code and a completely different section of your application is broken, despite the quantity of unit tests. So we have many things like this. We have many violations of the single responsibility principle. We have many pieces of spaghetti code. It's not that I hate spaghetti, right? It's just I don't want them in my code. Okay, it's all. So after analysis of all these problems, I came to the conclusion that it was all about architecture. That's how I introduced the concept of architectural bug. Okay, so at this moment, I also developed the conviction that if I could draw the data flow of my components, the probability to introduce a bug will be reduced to 0. Because in my opinion, a bug due to such a bad code can be often reduced to a data flow that is not properly identified. So since it was about architecture, I tried to read my old engineering lessons, and all I found was about UML diagrams, architectural patterns such as MVC, etc., solid principle. But I was not able to use them to help my junior developer. So I decided to completely, before that, all these tools are really relevant, but They require a great level of abstraction, and in the first place, and a certain experience of coding. So I was not able to use them with my junior developer. I started to look away to find something, a tool that could help me to describe the content of my components. So don't ask me why. My brain made me think about the biology. Okay, so I look at there. Just before biology, I wanted to focus on the architecture definition from Wikipedia, in which put an accent on sketching and building. Okay, so I was like, what is the equivalence of sketching and building in the programming industries? That's where I started to look at other industries, and in particular the biology one. If you look at this picture, you can see how biologists proceed to the dissection of the human body to understand its internal behavior. So I was looking the same thing, but for my components, and I was not able to find it. By the way, you understand now where does come from the anatomy in the component anatomy. So I keep on looking after other industries, and I came to the construction one. And as you can see, I'm not an architect. You are not an architect. But if you take a look at this house plane, you are able to understand what is being done here. Okay? You have a pretty idea of how the different structures will be arranged together to get the final result. You also have an idea of what kind of object you will be able to move inside the building through the doors and the windows. So that's it. This is the kind of thing I was looking for. So I keep on checking if there was not other similarities in both industries. And I noticed that in both industries proceed to sketching, to prototyping, and to building. But if you take a look at the construction industries, you will notice that at any moment of these 3 steps, you have a pretty idea of the internal behavior of what is being done, but not in the mobile application, not in the programming industry. So doing this comparison, I learned something that is really interesting, which is that unless you are skilled enough, the UML diagrams won't help you to design complex components. So there was a need here for a tool, a simple tool, a junior developer can manage easily. At this point, you could ask me, what happens if I'm not able to predict the behavior of my components during the design step? Why is it wrong? Well, I noticed that many developers will see the result of what they are coding only after many minutes or hours of work. So since many developers work without sketching, planning their job, it results in spaghetti code and many bad practices even for skilled developers, and that's a problem. So I keep on looking for similarities because I got that feeling that I was on something. Look at this beautiful mobile application. Okay, I'm not crazy, right? This is a mobile application. I will explain you why. When I see this building, actually, I see a set of functional blocks that communicate with each other. Okay, and by functional, I mean a specific action or a group or a specific group of actions. In the programming industry, we call it a use case, for instance. Okay. That's how I started to develop my conviction than building a mobile application was similar to building a digital house. Okay? So let's take a concrete example. The kitchen. At the house scale, the responsibility of the kitchen is to manage food. Okay? But at the kitchen scale, managing food doesn't make any sense since everything in the kitchen is designed for managing food. So there is a need here for sub-specialized function like freezing meals, stirring ingredients, or doing the dishes. Okay. Along with the sub-functions, the kitchen organization allows us to move humans, goods, waste, meals, etc. Okay? So by doing this, we just introduce the basics of the component anatomy that are the structures and the flows. And you have the same thing in your code. Let me show you how. Rooms and structures are similar to functions or components in your applications. Flows are your data flows. And in the flows, we have two kinds of flows, the explicit one and the implicit. The explicit are visible. That means in this room, if someone is crossing the room, you will see him. Okay? It's an explicit flow. So in the kitchen, you have humans, meals, waste, etc. And in your application, when you pass a parameter to a function, you see the parameter you are passing. So it's an explicit flow. But in the kitchen, you don't see water, light, or gas unless you play with switch, tap, and etc. The same way in your component, you won't be able to get the result of use query or use context unless there's hook are triggered at when the component is mounting. Okay. Donc the same way, we have tap, switch, and lamp to trigger the opening of water, light, and etc. The same way, we can send command with mutation, set state, dispatch functions. Okay. So let's take a break here. How can we profit of it? Okay. I told about the problems I had that led me to compare both industries, but I didn't explain what was my whole design process. It's really important to understand what follows. When I joined BAM, I have been taught to proceed like this. When you get the mockup, you divide it in horizontally, and for each part, you take the result of the UI workshop. Excuse me. Oh, sorry. You list mockup assets like images, icons, etc. You list UX behaviors like animations. You list backend dependencies like API calls. You extract the components and their properties. And in addition of this, you need to think about the existing code, the specific rules, and the side effects. This is a lot, okay? So it leads me to the first problem I noticed, a hard mental work. Okay. So to get out of this awkward position, you better develop a strong process to guarantee you won't forget anything. The second problem I noticed is the hidden complexity. If I can try this analogy, drawing the curves of a car, of a vehicle, won't tell you the complexity of its engine. Okay? So the same way, when you are using this approach, you know more or less how many components you need to develop, but it doesn't tell you how you need to develop this component. So there is a problem because we need to see the complexity, the whole complexity during the design step and not during the development step because it would be too late. Sorry. So to not be trapped by this kind of complexity, people used to make an exhaustive list of checks, like where does come from my data, what about the login state, are this component already developed, etc. Okay. but few people will ask about background behaviors, such as, do I need a context? How my login state is propagated to the views, how many formatters, adapters, or services are required. So where stands the complexity? The coupling is on alert. Okay, many architectural bugs comes with times in badly designed applications. They result in a poor ability of the tech designer to detect them during the design state. It does not mean the tech designer is not skilled at all. It just illustrates how complicated is it, how complicated it is even for a skilled developer. And the last problem is the lack of global architecture. If, for a reason, you want to go faster using parallelization, and if you don't pay attention to the global architecture, you will get 5 different architectures in the same screen, okay? And it's not really good for the code-based maintainability. So having this understanding of the construction industry in one hand, and knowing the problem I was facing in the other hand, I asked myself, what will happen if I turn my screen about 90 degrees, like in the Xcode render? Then I will be able to see the data flow crossing the components. That's it. That was what we were looking for. So I just had to sketch a vertical section of my components, turn it about 90 degrees, and it was done. So the 90 degrees to the left come from this operation I made to change my perspective when extracting informations from a mockup in order to develop the given component. So now you understand the origins of the component anatomy. Let's see together how does it work. Okay, the component anatomy is a design process with, in 3 steps, the layering one, the data flow analysis, and the fabrication plan. Let's have the change email screen. So the first step of the layering is to expose what I call the hardware context. Actually, if you rotate your mobile device about 90 degrees, you will notice that your JavaScript applications interacts with human sensor in one hand and captors in another hand through to what we call the bridge in the React Native. Doing that will help us to define 3 kinds of components. The UI one that interacts with the human sensor, the data one with the captors, and the business, which is responsible of implementing the business rule. And you can recognize a similar pattern in MVC, MVP, and other similar architectural patterns. Defining these 3 kinds of components will help us to clearly identify their scope in terms of architecture, because we are applying the single responsibility principle, only one reason to change. In terms of quality, because unit tests are simple to write, and in terms of maintainability, because there is no more space for spaghetti code. Sorry. So how to apply it? After having exposed the hardware context, we need to expose the layers. The rule is really simple. A component that contains another component defines a layers. So in this example, the change email screen will be the root layer, and we have a middle layer for the email form and a leaf layer. So behind the root layer, we have a background layer for the authentication context provider. This is one way to do that, but you can have a different approach. If, for instance, in your project you have an email field that will be used at any places, you can decide to create a layer for the email field, and this will be the way you do it. But for the purpose of this, this presentation, we will just keep the first model. So after having exposed the layers, we need to expose the components. Okay? To do that, we just need to encapsulate, to choose the way we are going to encapsulate the components in order to build them. So this step is really relevant because this is where you choose your component strategy according to the atomic design and the level of reusability you are targeting. You are also able to see the depth of your components. You can see the props drilling problematic. You can see the prop drillings in advance. You can anticipate the need for state management, and etc. And beside of this, I have my fabrication plan where I note in yellow boxes the different tasks I need to do in order to implement, to create or update this component, these structures. When we know which structure we want, then we can try to draw the data flow. How does it work? There is 4 kinds of data flow. We have the display data that go to the user, the event that come from the user, the request that go to the captors, and the response that come from the captors. Okay. So in our example, we are going to search for we are going to expose one event, and to do that, we are going to look at the mockup and see what component is able to trigger an event. In this case, we have the email input. So we draw a green row for the event with the circle that represents the handler function. And then after, we close the circuit, okay, by having a data flow that crosses at least two structures. So in this case, we know that an email input needs a state. So we invocate the setter, the circle in blue, from the unchanged handler, and the email state will iterate the email input. Okay, so we have a circuit. Closing the circuit is really important in the component anatomy because an open circuit represents an unachieved job or a potential bug. So closing the circuit guarantees you are controlling totally your data flow. After that, we can check the other side effects of this event, like the possibility to have an error text if the email is not correct. So from the unchanged handler, I will invocate the validate input function that will invocate the error state setter. Okay, but if you are a React expert, you can challenge this misconception because we don't need an additional error state here. Okay, actually, with the component anatomy, you can see why adding a useless state in the data flow is a bad thing. In fact, each structures involved in the data flow will increase the time response of the component. Okay, so will increase the time response of the component because each structures come with a response time cost due to the function stack, the memory allocation, and many other things like this. So I will fix my design and just invocate the validate input function from the email state and iterate the error text component. So I will do the same thing. I will keep on following the side effects of the same event to iterate the submit button, because the state of the submit button depends on the state of the validation of the email field. Okay. So when I'm done with all the side effects due to the text change event, I will restart the same thing with another event. So like this, I will draw any circuit that I need to do. And when I'm done with this component, I go to the parent, and in this case, I will define a use change email mutation that provides me a mutate function I will use to iterate the unsubmit property. And on success, I will invoke a function that navigates to somewhere I want. So this is the data flow analysis. By the way, you can see how why analysis the data flow is better than just divided the screen when you want to dispatch the work between many developers. Actually, relying on the data flow will help you to minimize the Git conflict, the number of Git conflicts. You will minimize the dependencies between the both parts, and you will maximize the parallelization between developers. So it led us to the third part, which is the fabrication plan, which consists in just reorganizing the different tasks I have collected in a graph of dependencies, and that's it. We are ready for the development step. For instance, this is an example of the fabrication plan we just made in my current project, where I was able to put 5 developers on 3 applications that communicate with each other. Okay, so the analysis of the data flow helps us to make it clean and to be confident in the development of that complex feature. So we are close to the end, and I wanted to share with you the potential usage of the component anatomy. Actually, you can use it to design a component, or just to have a technical discussion with other developers. You can use it to teach any component-based technology like React, Angular, or Vue.js to young developers that to help them to create a mental representation of what is happening into the code. You could even create a no-code app generator based on the Lego approach. And there is a last usage I wanted to show you, which is the computation of the architectural response of a component. Disclaimer, this is completely experimental, okay? It's not proven yet. But I have an intuition, I got an intuition. I thought that since component anatomy focused on circuits, I could then apply the same rules than to electrical circuits, okay? And one of these rules is the possibility to compute the time response of an electrical circuit. So it could help us to define a new unit that we could call the architectural response, which is defined as the time response of the equivalent circuit, and will measure the inner component performance. Okay. However, computing the architectural response of a given component will require to know the weight of the structures involved in the data flow. Okay, so the same way we have the impedance of a component in an electrical circuit, we could define a second unit, which is the structure impedance or the structure weight. And we could use the cyclomatic complexity or any arbitrary number according to the strategy, your computational strategy. And this element will will measure the component performance when invoked by another component. By doing this, we have just introduced a new formula, sorry, that say that the architectural response is a function of the different structures' impedance. And you can recognize that it's just a generalization of the known function UI equal function of states. So how can we, I was thinking about a practical thing, and I was like, if we could have a VS Code plugin that compute the architectural response in real time, it could be really good, because during the development step, you could define architectural rules the same way we have linter rules, okay? And one of this rule could be for any component, if my project, I want them to never reach a threshold or a certain value, okay? So it could be really interesting for people interested in the architecture, and it will avoid to have to put so much energy in optimizing application after we have been developing them. So I received feedbacks from many people, and Antoine T, a developer at BAM, told me that he was able to reduce his coding time from 1 hour to 10 minutes, because he took the time to draw the complexity of the component, and after that it was really easy. I got other feedbacks that told me that after been using the component anatomy, it was really easy to plan a collaborative work. And another example is one of the dev of my team who was not able to design a complex form. So after we draw the data flow of the component, he was really confident, she was really confident, sorry, to develop the component. So that is. Yes, I started to create a kind of standard of the symbols I use in the component anatomy, because I received other feedbacks that told me, oh, it could be great if any developers could use the same symbols to understand the same thing, that avoid confusions when we are reading the document. It is available on my GitHub account. It's totally experimental for now, so if you want to develop your own convention, be free to do that. So in conclusion, in this talk, I show you how I tried to solve my initial problem as a tech lead, and then how it led me to build an approach that it integrates the component design thanks to the structures. It takes in account the testing consideration, and it provides a better scheduling of tasks based on the analysis of the data flow. Working on this method taught me that a big part of problems we have when going in production are often linked to the architecture. So I think about performance issues, architectural bugs, issues with the job parallelization, and many things like this. So keep an eye on your architecture. I don't mean the folder architecture, but the real architecture of your application. And maybe you will be better in what you're doing. So to be honest, I don't really know where I'm going with this experimental method, but I know for sure I will keep on working and improving it while it helps me to be more efficient in my work. Thank you for your attention.